Hi, I'm Chem's best friend. If you would like to contact me, the information is on the bottom of your screen. Hello and welcome back. The story continues. Where are the electrons in an atom? In the last video, we went over the Bohr model of an atom, which is a very planetary model, where he puts electrons on specific orbits, and if they absorb energy, they can move farther away from the nucleus. But electrons are attracted to the nucleus, so if they jump down energy or jump down to a lower orbit, they release energy. He explained the emission spectra of hydrogen atom. But he didn't explain it all. There were still questions remaining. So, are you ready to hear the story? Here we go. Let's go to my screen. So today we will talk about the whole wave behavior of matter. So the next person that picks up after Bohr is Louis de Broglie. He's a French aristocrat, and he comes up with a crazy idea and an equation that actually works. So if light, which we always thought is a wave, is also a particle, that's what Einstein said, right? And he gets a Nobel Prize for saying that light is a particle. De Broglie asks, can particles be also waves? He's turning everything upside down. What is he doing? He actually comes up with this amazing equation that works. So let's look at this a little bit. So here is wavelength. Here is the wavelength, right? So if can particles be waves? So we have Planck's constant, which is, remember, it's a very, very small number. It's 10 to the negative 34th exponent, tiny number, over mv, where m is the mass, kilogram of this particle, and v is the velocity of that particle. Well, if you took physics, mass times velocity is momentum. That's a very specific thing about a particle, right? So particles have momentum. And now he says these particles take Planck's constant divided by momentum, you will have a wavelength of that particle, which is crazy. But how is this helping us answer the question? Where are electrons in an atom? Where is this going? Let's go. Let's talk more about de Broglie's equation. So what does this exactly mean? Let's try it. So let's pretend we have a grapefruit, 1 kilogram grapefruit. It's a little big, but play with me. 1 kilogram grapefruit rolling in 1 meter per second. What is its wave function? Well, mass 1, velocity 1, its momentum will be 1, yes? So the wave function will be Planck's constant, which is 6.626 times 10 to the negative 34th, and will be meters. Well, what does that mean? Well, the size of an atom is in angstroms, which is blah, blah, blah times 10 to the negative 10th. So we have 10 to the negative 10th compared to 10 to the negative 34. So that means the wave function of a grapefruit rolling at 1 meter per second is smaller than the size of an atom. So do you think we care that it's a wave? No, it's too small to even matter. But what about an electron moving at 5.97 times 10 to the 6 meters per second? What about that? Well, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. And here is its, its velocity. And we plug this into that equation, de Broglie's equation. And here is, I'm just trying to do some unit conversions here. Right, so 1 joule is the, flip it, what the conversion is. And we're going to say that the wavelength then of this electron moving at this speed is 1.22 times 10 to the negative 10 meters. Or 1.22 angstroms. That's in the X-ray region of an electromagnetic spectrum. 1.22 angstroms. That's not nothing. So what did he say? That means electrons behave as waves. Electrons can behave as waves. Their mass is so small that actually this wave, they do behave as waves. It becomes important. Wow. Wow, where does this story go? Well, around the same time, Werner Heisenberg comes up with Heisenberg's uncertainty principle. What does he say? So he says it was impossible to know at the same time the position and momentum of a particle. The more accurately we know one of these properties, the less accurately we know the other. He comes up with another equation. Well, it's very hard to explain, but in a simple terms, I want you to think of billiards. I want you to think of a pool table, and we're going to have a game of pool. You are outside my classroom and I blindfold you. And then inside the classroom is a pool table with two balls, the white cue ball and let's say one red ball. And I'm going to ask you, please tell me, where is the red ball? So you come in blindfolded and you can feel out, and I will show you where the white ball is, and then you take that stick and you hit the white ball. How do you know when you hit the red ball? Well, you will hear a noise, yes? So on top of it, I'll give you superhuman powers. You'll be like a Superman, Superwoman, and your Superman power is echolocation. You will know exactly where the white ball hit the red ball. And you can come back and you will say, this is where the red ball was. Right? But the act of hitting the white ball, hitting the red ball, moved the red ball. So you will be able to tell me where the red ball was. But I didn't ask you that question. I ask you, where is the red ball? Where is it? Right now. You cannot tell me, because the act of hitting the red ball moved it. So that's the same idea here. If you try to find out where electron is, they are so small that the only way of telling where the electron is by hitting it with another electron. But the act of hitting it will change its position and momentum of that electron. So it's summarized like this. If we know the position of an electron, we do not know its momentum. We do not know which way it's going. If we know the position, we do not know which way it's going. If we know which way it's going, we do not know its position. This is what we want, and it's impossible. We want to say electron is here, going this way. This is impossible. He says we will never know that. Why? Because remember, electrons, de Broglie told us that the electrons can behave as waves. All right. Around the same time, there also was this double slit experiment done. So if I have two slits and I shine electrons and then I look at the pattern, well, imagine throwing some, golf balls or marbles through two slits. You would expect the pattern to be right there. They will hit two spaces. But we actually get this pattern. The middle is darker, and when the color fades, we get this interference pattern on the screen. And people who know waves, this tells them it has to be a wave. Because this is looking from above the double slit experiment, you are looking above, you will see that waves, right there are areas where waves can be added together, and there are areas where waves interfere with one another. This is, where they interfere, and this is where you can add them up. So what does this mean? That means electrons do behave as waves. They actually had the experiment telling them. What does this mean? How do we put this all together? Well, Erwin Schrödinger comes up with these wave equations of an electron, because, and he called these wave functions. It's very, very complicated. We will not try to go into it. But Schrödinger is also thinking, so if an electron moves, does it spread out? Does it become a wave? Is this what it means? And if this is what it means, how do we know where electrons are in an atom? This is really, really strange. Schrödinger and Max Born actually come up with this. So if you take Schrödinger's wave equation, here is that letter psi, Greek letter, this letter psi. And if you square it, you will get probability density of where an electron is most likely to be found. And this probability means orbitals. Please do not get this confused with orbits. Orbits are not orbitals. Orbit is a circular path, a set distance from the center. That's what Niels Bohr said. That's the planetary model. This is orbitals. Orbitals is math probability, a 3D regions of probability where an electron is most likely to be found. So that means he's looking at this, he has this probability, he has this math probability, and he sees that there are regions where probability actually goes to nothing, to zero. So he says, aha, these probability areas, they are different shapes. So there's a circle area, there is the dumbbell area. Like, remember, these are math 3D shapes. Here is some other probability areas. We call them d orbitals. These are f orbitals. He has these 3D shapes of where an electron is to be found. So he recognizes that they are like Russian matryoshka dolls. They stack one into another. And there are areas where probability goes to zero. So he says, aha, this math tells him that Niels Bohr was not completely off. Remember, his model still works for hydrogen. So the orbits are wrong, but these energy layers stacking into one another are correct. So these energy layers are all correct. So these energy layers all stack into one another. And he has, here is this one probability area. Here's another one. You can keep going with a third one. And they stack onto one another. So where does he get these? Where does he get these shapes? Well, math tells him that. So it's a very complicated mathematical equation. But he says, he calls them quantum numbers. So just like in your math class, you might have x, y, z variables. He has n, l, m of l, and m of s. These are like his variables in his equation. And here is what we will quickly go over. So n is your principal quantum number. These are your quantum numbers, your principal quantum number. This can only be positive integers. 1, 2, 3, whole number integers. That's it. And they tell you energy level, right? So they tell you energy level. So here is 1, 2, 3, 4. Yes? Then he has angular momentum quantum number. That's going as L. It can go from 0 all the way to n minus 1. These are the constraints that math tells him, right? These constraints in his equation. They tell us the orbital shape, which is also our sublevels. Then he has magnetic quantum number, m of L. Well, they have to go from negative L all the way to positive L in whole number integers. What does that tell him? That tells him orbital orientation, 3D space orientation of an orbital. And then there's spin. And spin, everything has to be either positive half or negative half, and this is electron spin direction. It's like, think about this, you can spin this way. I can either spin this way, or I can spin this way, right? So electrons can spin. He comes up with this nice table that summarizes it. So here is the principal quantum number, and now we have angular momentum, our sublevels. So if you have n, remember L goes from 0 to n minus 1. It can only be one sublevel. Energy level 1 has one sublevel. And we call this S. So 0 corresponds to S. Then energy level 2 can have two sublevels. Energy level 2, two sublevels. And the values of magnetic was quantum number, which is your space orientation. Here's 1 or here's 3. So that means 0 corresponds to S. 1 angular momentum corresponds to P. And there is 3 different ways of putting a p orbital into space. So we have 3 p orbitals. We have 1 s orbital and 3 p orbitals. So energy level 1 can only have an s orbital. That's it, s orbital, one of them. Energy level 2 can have s and p, and there is one s orbital and 3 p orbitals. Okay? Now energy level 3 can have 3 sublevels. And the value for your magnetic quantum number, well, 0 corresponds to s, 1 here corresponds to p. There is 3 different ways of putting p in space. 2 will correspond to d orbitals, and there is 5 ways of putting them in space. This is why we have 5 d orbitals. Right? Energy level 4 has 4 sublevels, and we have 1 s orbital, 3 p, 5 d, and 7 f's. Now, this is your total number of orbitals if you add these numbers together. And remember, there was also a magnetic spin quantum number, which was 2. So you can, 2 electrons go to each orbital, and here is your number of electrons in each energy layer, in each level. Now, what does that mean? It just, remember, this is math, this is probability. So here, one more time. So s orbitals can be only one way of putting them in space, and they are spherical in shape. There's only one way of putting a sphere 3D into space. Here is 3p orbitals, and they are dumbbells. So you can put it on x, y, or z axis. So there's 3 different ways of putting p orbital in space. Here are our 5 d orbitals. D orbitals are 4-leaf clovers. And there is 5 ways of putting this shape in space. And then there's one little one because it couldn't fit. There is 7 f orbitals. They look like this. Sometimes they are like a double 4-leaf clover. And there is, 7 ways of putting this f orbital in space. This is why there's 7 of them. So these are, remember, probability density of where electron is most likely to be found. We will never know exactly where an electron is, but we can tell where an electron is most likely to be found. Now, this was really interesting because Albert Einstein couldn't accept it, but it's all probability only. He then says this famous quote, "God does not play dice." Because in the game, any game, if you play with dice, it's all probability. So this is really interesting. That electrons, we will never know where electrons are. We can only find out with probability where they are most likely to be found. So where is this table? What will this tell us? How do we deal with electrons? Where are they? That's the topic for next video, where we will actually learn how to do electron configurations. How do we assign addresses for electrons? How do we give them probability addresses? So thanks for watching, and see you next time.